in the last lesson, we were doing these Venn diagram type questions. And I just want to start with, can you do this question by yourself? So these are ways of getting to school. The one is by car. So C is by car. W is walking. And B is by bicycle. Here is a Venn diagram. Can you answer the questions 1, 2, 3, 4, 5, and 6? Because in the last lesson, we dealt with these 3 Venn diagram events. And let's just start with the first one. Can you tell me what is the probability that a randomly chosen learner walks to school? And we know that all probability questions are about favorable over possible outcomes.
Mr. S?
Yeah.
Is it possible that you can maybe zoom in a little bit on the questions?
Okay, absolutely.
All right, thank you so much.
Maybe make this bigger. And I'll put that up there. And I'll make that even bigger. So hopefully that helps out a little bit. So I guess, first of all, we need to figure out like how many people are involved here, or what we might call N of S. How many people are involved? And what you need to do is you need to add up all of these regions. And so for this question, 162 is going to be an important number. Now, if I want to know what the probability of someone walking to school is, and we might indicate that like this, we need to know what that number is. So what's that going to be? So it's not 17 because it says walks, but you're on that would be walks only. So what you need to do is you need to add up all of those things that are inside of the walks circle, and that would be 69 out of 162. Yeah. So it's quite likely, I mean, you could put it into decimal if you like, but it's pretty close, it's almost close to like 40, it's getting close to 50%. Okay, I want to know what the rest of these are. You can put your answers below. So I get 80 for the probability of using a car. For bicycle, I just need to really look at the circle here. So 79. Okay, so we've done. What about walks only? What's the probability I get someone who only walks to school. That's all they do. They never take a car. They never use their bicycle. Well, that must be this region over here. And so that is going to be 17. What is the probability that the person never walks to school? So what that is like, it means you may not be in the W circle. You can only be out here. Or you could be here, or you could be here, you could be here, but you may not be in the W circle. Now we know how many people there are in total, so we could actually just go 162 minus whatever the number of people who walked was, which was 69, or we could literally count up all of these. And what do you get? You get 93 out of 162. Last one, what is the probability a randomly chosen student walks or uses a bicycle? So what would that look like in terms of the region? So walks or uses the bicycle. So either of those, it's not and, it's like walks or. Both of them are favorable outcomes for this probability question. So we go 20 plus 22 plus 19 plus 18 plus 17 plus 15. What are we getting? Ooh, walks or uses a bicycle. No, so because this person uses a bicycle, these people use the bicycle sometimes. I like your question though, Awami. It's a good one. So Awami's asked, wouldn't the 20 from the car not be included? Here's the thing. If this person uses a car sometimes and a bicycle sometimes, they still use a bicycle. So the question was asking, how many people walk or use a bicycle? And so as long as you're inside these two things here, you're fine. But it's a good question. So thank you. Lovely question. We learn so much from each other's questions. So that's why I always encourage students, they mustn't, even if your question is wrong, or you get it wrong, it's not really about that. You learn a lot by doing it. Okay. Thumbs up if, yeah, Sate, yeah, what is your question?
Say, I wanted to ask if when they say the probability of walking or using a bicycle, won't we use 22, 18, and 17?
Okay, so you're thinking, okay, these people all walk to school at some point. Like these people walk and use a car. The 19 use all three methods of transport. 20 of them use a car and a bicycle. But remember, when the question is asked, we're saying, I'm choosing one random person from this collection of 162. Now, if they either have walked to school at any point during the year or used a bicycle, that is considered a favorable outcome. So as long as I get someone in one of these regions, I will have someone who walks or uses a bicycle, or maybe they use more. Does that help a little bit with my understanding it?
Yeah, so I think by my understanding, you mean that by in 15, 19, 22, 18, and 17, that's where
Perfect.
walking occurs.
Couldn't have said it better myself. Great question, Sati. Okay, now let's move on. This is one type of exam question, but the other one we were doing at the end of the last lesson was, I don't give you the Venn diagram. You have to draw it for me. So what I want you to do is step one now is there's a whole bunch of information, and I want you to draw a Venn diagram as best you can to represent this information. I'll highlight something important. There are 174 learners, and there are also 8 who prefer all 3 sports. And so because there's 8 who prefer all 3, you must have the circles that intersect. Draw me the Venn diagram as best you can and say done when you are done. And if there's a question, I really encourage you to put your hand up and we can chat further, but over to you to try and do this one. Let me redo that. It's very hard to do these 3 until you've done these ones down here. So my suggestion would be to focus on doing, let's say that one first, and then that one, and then, oh, this could be X prefer chess and swimming, but don't like boxing. Suppose I should put that on. And my drawing's a bit small, so let me redo it. And we said that was 8. So I'm going to cross this out. And then I'm going to actually do the X, because this is X prefer chess and swimming, but not boxing. So that must be up here. I'll cross that out. And then it says 18 prefer swimming and boxing. So swimming and boxing would be this region over here, but there's already 8 in there. So this is going to be 10 to make up the 18. That's a bit sneaky. Give me a thumbs up if you understand why, if it says chess and chess and boxing, is this region, sorry, not, is it chess? 18 prefer swimming and boxing. So we know that that region, but there's already 8 in there. Okay, so I'm losing a couple of you. So let me slow down. So if you look at this, there's already 8 who prefer all 3 sports. Now it says 18 prefer swimming and boxing, okay? And the swimming and boxing region is going to be here. These are the people that prefer swimming and boxing. It's that whole region. Now, you know there's 8. You know in total it must be 18, which means that must be 10. So just take a moment to think about that. Now, using the same logic, 27 prefer chess and boxing. So chess and boxing. What do you think is going to go here? What do you think is going to go in that square box I just put there? Now, you know there's 27 in this region. Now, what does that mean this has to be? This has to be 19. Okay, so 26 do not like any of the three. Well, that's easy. That's just outside. So you need to find me this one. I'm guessing it's got to do with chess. So what do we think goes in this one over here? Now, you know there should be 90 in this whole circle, but I want to know just this region. So it's 90 minus 19 minus 8 minus x, which gives me 63 minus x. Okay, what do we think is going to go here? Try and work that out for me. So since we're subtracting 8 from the intersection, why don't we say x minus 8? Paul, so what we have to do, I kind of get what you're saying, but you don't want to, if you can fill in a region, I think for now, I'm not going to go down that rabbit hole right now. So we're just following that particular process. It's mainly because it wouldn't be useful information to answer your question. Okay, here we'd go 64 prefers swimming. So I'd go 64 minus 8 minus 10 minus x, and we get 46 minus x. And then what about down here? What are we going to get down here? This is for boxing. Oh, well, following the same idea, I would go 77 minus 19 minus 8 minus 10. And I am getting 40. Yes. Fantastic. Now I have a problem, ladies and gentlemen. That is my Venn diagram, right? So I'm all good, fantastic. But the second question says, calculate the value of x, the number of learners who prefer chess and swimming, but not boxing. What am I going to need to do in order to find out what x is? I've used up all my information. So how am I going to get what x is? What pieces of information could help me, do you think? Add all the values. Okay, so I'm going to add up all the values, and what are they going to be equal to, Tebogo? Owami has said 174, and that makes sense because there are 174 people in here. Yes. So I'm going to go 63 minus x plus 46 minus x. Maybe I should even tick this off. And then I'm going to go plus 19 plus 8 plus 10. And then I'm going to go plus 40 plus 26. Can you find what the value of x should be for me? So I guess I have to cross out that and that. And I've got to get a total for all these numbers. My total is 212 minus x. And then if I move that around, I should get x is 38. Yes. Now, why is this fantastic? Well, it means that we no longer have to have a variable up here. We can fill in what the answer to that is. And it was 63 minus x. So 63 minus 38 means this must be 25. This must be 38. And 46 minus x, 46 minus 38 is 8. So can you tell me, last question for this sub-question. Oh, let me bring that back. Can you tell me the answer to this question? What is the probability that a randomly selected learner prefers two types of sporting codes? Write the percentage, write the answer as a percentage correct to 1 decimal place. What about the other x? Andile? So what happened was, in the process of minus x plus x, it got knocked out. And so we only had to focus on the minus x that was left behind. So they got cancelled out. Does that help, Andile? Let me know in the chat. There were 4x in total. So it was just this one over here, this one over here, and this one over here, if I remember correctly. So what is our calculation here? We're going to have 174. I'll try and get back to you, Andile, if I can, to try and understand your question. At the moment, I'm not getting exactly what you mean. They were 4x is total. Okay. 174. Okay, now, what regions are people who like two types of codes? So it can't be the 8 because they like 3. It has to be, these people like swimming and boxing. These people like chess and boxing. And these people like chess and swimming. And so the probability of choosing someone who likes 2 sports is just going to be 38 plus 19 plus 10. And you should get 67 out of 174. And that is going to be to 1 decimal place, round, it's 0.385, blah, 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 which is going to round to 0.4. Because it was saying 1 decimal place. All right, let me know in the chat, thumbs up if you are following the Venn diagram. So basically, why do we do Venn diagrams? We do them to help us imagine the possible outcomes and the favorable outcomes. So they're a way of understanding the relationships within groups. And what we tend to do is really just work from the inside out to fill out the different regions that are possible. And so, yeah, that is, I would definitely recommend, you can practice them more in the quiz, but we're basically going to move on from Venn diagrams in the second half of today. But yeah, let me know in the chat, thumbs up if you're feeling okay on Venn diagrams, thumbs down if you're feeling a bit lost. Okay. Cool. Well, you know what time it is. It's break time. So I want you to stand up. And we're not going to go too long today because I want to get into tree diagrams, but let's just do a quick little roll of the shoulders. And roll forward. Let's do a little bit of rotation. Okay. And let's just do a tricep. Okay. And let's do some jumping jacks. We haven't done them for a while. So we're going to do 20 jumping jacks. 3, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, halfway, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we are good to go. Okay, well done, everyone. I see my screen has decided to be difficult. Let me just turn that back. And here's your little brain break for today. The brain break is Maths 24. So can you get to 24 using any of the 4 combination numbers here? And let me know in the chat if you are, if you think you've got it. Oh, I feel alive. I feel the blood pumping through my body, which is good. Well done, Irene. Well done. Do you feel good too? I feel a little bit out of breath, but my body feels like it's awake. Okay, Oratile, let's have a look. So Oratile said 8 minus 4, which gives you 4, no, yeah, times 6 minus 3. Hold on, I don't think that gets us there. 8 minus 4, because that would give us 4 times 3. Yeah, so that doesn't quite work, I don't think. What we could do is don't worry, Oratita, that's fine. Nkosi has said, what about 6 times 5? So 6 times 5, which is 30, minus 7, or minus 7 minus 1. So it's basically 6. So you're absolutely right. And Lebo agrees. So it's 5 times 6 minus 7 minus 1. So the hardest one went the quickest today. Well done. What about blue and red? Can anyone get me blue and red? So Andile has said 8 minus 6, which gives me 2. Well done. Times 6 times 2, which gives me 24. Nice, Andile. That is awesome. And what about the red one? That's normally the easiest. Is this catching us? So there's a 6 and 8, a 3 and a 4. How about 6? My tip is 6 divided by 3 is 2. Now, how can we use that? 6 divided by 3 is 2. That's what I was thinking to help us out. How do we get up to 24? Rafensa has said 4 times 3. Oh, it is even easier. I don't have to do my fancy one. 8 minus 6 is 2. 2 times 3 times 4 is 24. Nice, Rafensa. I like it. And I hope that everyone enjoyed their break. We are going to head back to the land of probability now. But yeah, that was fun. Maths 24 is always fun, especially if you haven't done it for a while. Okay, so we've been studying probability for a while. We learned about the basics, we learned about identities, and then we started learning about structures that help us visualize outcomes. And so a tree diagram is another way of visualizing different possible outcomes. And they're often useful when we are dealing with independent events and dependent events. So I suppose that's a bit of a broad statement, but that is true. So let's go to an example to help us understand this. So suppose a family has 3 children. There are many combinations of boys and girls that can make up the 3 children. Now, if you try to use the Venn diagram idea for this, it's just not going to be a good tool for the job. It's like when you're trying to you know, I don't know, you're trying to change a tire and you've got, you know, a spanner. You know, it's nice that you have a spanner, but you'd much rather have a jack and, you know, the relevant tools for the job. So you have to learn how to use the correct tools. So to draw a tree diagram, what we do is we say, look, given a situation, what are our first choices? So if you're having children, your choices are boy and girl. And that would be for your first child. But you may have a second child. Okay, so first child. Now you may also have a second child. And if you do that, you have the possibility of boy, girl. So we'll say second. And then for the third child, well, you have the same two choices all over again. Now, this is what we call a tree diagram showing you the different combinations. How many different possibilities are there for having 3 children? How many different gender combinations are there? What do you think based on my drawing? What we might call, what is the N of S for the sample space? Like how many possible outcomes are there? Well, you can kind of see them, hey? You can see boy, 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 girl. There are 8 possible outcomes. Yeah. And this is one of the strengths of a tree diagram. It's just so visually clear in the way that it describes this uncertain event of having children. Now, the other thing that we tend to do with a tree diagram, although it's not as relevant in this case, but we write the probability of that event happening on the tree, on the branch. So the probability of having a boy is 1 in 2. The probability of having a girl is 1 in 2. And in fact, because these are equally likely, all of the branches would have these half and half. But if you have events where the one item is more likely than the other, the split won't be 50-50. The split will be like 30-70 or whatever it would be. So when drawing a tree diagram, you start by drawing the branches with the outcomes, and then you move to writing the probabilities on the branches. Now, let's answer some questions. Use the tree diagram to work out the probability that all children are girls. So what is that going to be? What's the probability that all of the children that are born are 3 girls? I have a friend who has 3 daughters, so it does happen. And what do you think the probability of that happening is? So what is the probability of G? Well, there's 8 possible outcomes, and only one of them is the favorable one that you want in this question. So you wanted that one. So it's 1 in 8, or in decimal 0.125. Now, one of the cool things about tree diagrams is you can see that 1 out of 8 options is the correct way to do it, but you can also multiply along the branches. So another way of getting to that answer would have just been to say, well, the probability, because these events are independent, okay, and we'll talk more about them in the next lesson, but you could have also done a half times a half times a half to get the probability of that event happening. We'll see that more in the next example. Okay, what is the probability that all 3 children are of the same gender? What do you think the answer to that question would be? So this would be like B, 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 or G, G, G. Well, boys, boys, boys. So you can see that there is a 2 in 8 chance, or if you were using that method, you could just say it would be a half times a half times a half for the girls, plus a half times a half times a half for the boys. And you would get the same answer of 2 out of 8. I'm going to miss out this one because it's not particularly helpful, but let's do the last one here. The probability that one of the 3 children is a girl. What is the answer to that? That the probability that one of the 3 children that you have is a girl. Now watch out. It's only, you can only include favorable outcomes where you have one girl in the family. So it can't be this one. Can be that one. Can be that one. Can't be that one. Can be that one. Can't be that one. Can't be that one. Can't be that one. So remember, it's not having 2 girls or having 3 girls in the family is not a favorable outcome. That one of the 3 children is a girl is a favorable outcome. So what is my probability going to be? So I think it's always going to be out of 8, and there's 3 ticks, so it's 3 out of 8. Give me a thumbs up if you followed my logic on the tree diagram. Give me a thumbs down if you're feeling a bit sketchy on these tree things. Okay, so again, all that a tree diagram is trying to do is help you to visualize the outcomes. And I can see that quite a few students are still feeling unsure. So let me do another example. If you are unsure, you can always come back and watch the repeat of the video, but you'll see the next example, you'll see some kind of similarities. So before we start answering this question, I just want to set it up for you. Okay, so just hang in there if you're unsure. I promise each time we do a new example, it will get easier. So it says, a bag contains 5 red counters and 3 yellow counters of the same size. So me draw a bag. And in the bag, there are 5 reds. So let's go red, 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 red. And there are 3 yellows. So yellow, yellow, yellow. So that's what's in. And you are picking from this. So let me draw a hand. And this looks like a bit of a monster hand, but anyway. So you're putting your hand in there and you're grabbing from the items in there. But you pick it, a first pick, and then you replace it back in the bag. And then you pick a second time. So you have to draw me now a tree diagram for choosing once, putting it back, and choosing again. So can you try and draw a tree diagram for me that represents that situation? And what I want you to do is I want you to think, what are the possible outcomes for pick 1 and for pick 2? And then I want you to think, what are the probabilities you should be writing on the branches? I'm going to give you 2 minutes now. And when you feel like you're done, I want you to say, done. And if you are unsure, I would love to hear from you in person or in the chat, and we can discuss this further. What are the possibilities when I'm picking from the So I know there's red. I'll use green for yellow. And I know there's red, green for yellow, red, and I'll just use that. So now I need to think about what are the probabilities on this branch. So what do we think the chance? I think this is a 5 in 8 chance, and this one is a 3 in 8 chance of occurring, because there's 8 things inside. Now, if I take something out and put it back, what is going to be the probability of getting a red on the second pick? Well, because I put it back, it feels like it's exactly the same. So this should be 5 out of 8, and this should be 3 out of 8. And this should still be 5 out of 8, and this should be 3 out of 8. These are independent events because, you know, essentially you've put this back, and so everything is the same. So your tree diagram should look like this. It should have these branches. Now, let's answer some probability questions about this. So if I say to you, what is the probability, so this is question number, that a red counter was first picked, followed by a yellow counter. So what is the probability of red and then yellow using your tree diagram? Now, remember, if you want, yeah, actually, I'm not going to say anything. I want you to try and work it out. What do you think the probability of choosing a red counter on your first pick and then a yellow on your second pick? Put your answer in the chat. So which one would it be? It would be red and then yellow. Now, here's the thing that's sneaky. These are not equally likely outcomes. There are 4 outcomes, but they're not equally likely. It's far more likely that you will get reds when you pick out of here. So we can't just count that there are 4 outcomes here and say, never. What we have to do is we have to use that method where we multiply along the branch. And so what we say is we say 5 out of 8 is the chance of getting a red. And then the chance of getting a yellow is 3 out of 8. And we multiply and we say there's a 15 out of 64, or if you were using decimals, there is a 0.234 and so on. So once the outcomes are not equally likely, we can't just count the outcomes like this with a tree diagram. What we do is we multiply along the branches. Give me a thumbs up if that kind of, I mean, if you understand the idea. You may not like it, but that is the most efficient way to calculate, because we no longer have a 50-50 split. Give me a thumbs up if you are with me. Give me a thumbs down if, okay, I will repeat. If I want to know the probability of getting a red counter followed by a yellow, that is this pathway. Now you can, I thought some of you would say the answer is 1 out of 4, because there's 4 possible outcomes at the end here. But the problem is that getting red is far more likely than getting yellow. So we can't just count and say 1 out of 4 or something like that. To get the probability of an outcome, we actually multiply along the branch. So to get the probability of a redder than a yellow, we go 5 out of 8, which is the probability of getting red, and then times by 3 out of 8. And then we went to that. Okay, now let's do the next one. What is the probability that a yellow counter was picked first, followed by another yellow counter? What do you think the answer to that is going to be? In probability notation, I would call this like that. Now, which pathway would I be looking at? I think it's that pathway there. So if we follow the rule that if we want that outcome, we can't just count when they're not equally likely. So we go 3 out of 8 times 3 out of 8, and I get 9 out of 64. Yeah. And this makes, if I put this into a decimal, let's see what I get. So I get about 0.14, which it makes sense that this is less likely than the previous one because there's less yellows inside. You would expect this to be smaller than the red-yellow option. Okay, let's do, what is the probability that a yellow counter was picked first, followed by a red counter? So yellow first and then red. So yellow and then red would be so there should be a 15 out of 64 chance that you get yellow and then red. Now, I want to spice this up because I can, and I want to ask you a bonus question. What is the probability that you get counters that are the same color? That you get two counters that are the same color. So you either get red, red, or red, red, or you get yellow, yellow. So what is the probability that when you draw out the thing, you always get the thing that's the same color? What do you think the probability for that would be? You're going to draw the same color twice. So it doesn't matter if it's red, red, or yellow, yellow, but either of those are a favorable outcome. What do you think the answer to that is going to be? So we know it's going to be for red, red, it's going to be 5 over 8 times 5 over 8. But that's not the only one that's favorable. You could also get yellow, yellow, which is 3 out of 8 times 3 out of 8. What is the probability that you will get ones that are of the same color? Okay, be careful here, because you're going to get 25 out of 64 for this, and you're going to get 9 out of 64 for this, which then gives you 34 over 64. And that would give you 17 out of 32 if you simplified. Or in decimal, it would give you 0.53125. So there's actually a greater than 50% chance that you will get the same color on both tries, is what that's saying. So it's actually more likely than not that you will get something of the same color. Give me another thumbs up, thumbs down about understanding how tree diagrams work. Okay, let's squeeze in one more before we finish tonight. I want you to draw me a tree diagram to represent, so there's a bag and it's got 6 blue, 5 red, and 9 white. A white marble is drawn and then replaced, and another marble is then drawn. draw the tree diagram for this. We're not going to answer the question now. I just want you to try and draw the tree diagram for me. And just say done in the chat when you are done. I just want you to get a bit of practice drawing the tree diagrams. Actually, let me make this a bit bigger. Now, what do we think the probability of getting blue is? Well, we need to know how many marbles we're dealing with. So 6 plus 5 plus 9 is 20. So when I say what's the probability of getting blue, it's going to be 6 out of 20. For getting red, it's 5 out of 20. And for getting white is 9 out of 20. Now, what's important is because I'm putting it back, none of these probabilities are going to change. So I get 6 out of 20, 5 out of 20, and then 9 out of 20. This is for my second round pick. 6 out of 20, 5 out of 20, 9 out of 20, and then 6 out of 20, and 6, 5, and then 9. Oh, this is too nice to not do now before we finish. So what is the probability, using this Venn diagram, that both marbles are white? So what is the probability that both marbles are white using this tree diagram? What do you think? Look at the drawing and see if it can help you. Which path do you think it is? This would be such a mess to try and figure out just in your head, but a drawing can make things so much easier. What do we think the probability that if we're picking two, we're drawing the marble and replaced, and then you draw again, what is the probability that you get a white marble and then another white marble? Okay, it's not going to be 1 out of 9. Be careful, because there are 9 outcomes, but they're not equally likely. What you need to look at is you need to look at that branch and that branch. But what do we do, especially when they're not equally likely? It doesn't make sense to count 1 out of 9. What do we have to do? We have to multiply along the branch, and we're going to get 9 out of 20 times 9 out of 20, which is 81 out of 400. And so that is going to be approximately 20%, or 0.2, 0.2 and 2025.